our satellite image. First of all, you start from the image. So what do you have on the image? You have the sample and line. You have sample and line. And this sample and line is, you have the perspective center, and then on your image, you have a sample. You have a perspective center over here. And this is the image plane. This is the image plane. And you are pointing at any sample and line location on the image. And what you want to know is this unit vector, this observation vector. So we call it ULOS. LOS means line of sight. Line of sight. So the answer, what you want is this. And this can be described with these two components, psi x or psi y. So this is your perspective center. This is your perspective center, and z-axis for this line of sight system. For this line of sight system, the z-axis is your camera axis. Z-axis is your camera axis, and x and y, that's your image coordinate. Well, you can say axis. So in this case, what you want to derive is this observation vector in this line of sight coordinate system. In this coordinate system. So how to derive the psi x and psi y? You can use the line of sight third order polynomial function, which is derived from the IOP, from the the camera interior orientation parameter, including, for example, like the focal length and then the size, the image size, and the image size. So those are the information you will need to create this line of sight third order polynomial function. But with that, if you have the input of simple and line, then you can obtain psi x and psi y. And psi x and psi y defines this unit observation vector, the ULS, U line of sight. Okay, so imagine right now this vector is in the space of the line of sight system, and this line of sight coordinate system is by using the perspective center as the origin. The perspective center as the origin with this z as the camera axis, and x and y coordinate system for the image space. Okay, so it's in that space. So eventually, we want to talk about the observation vector in the Earth-centric framework, so that we can integrate with other vectors, because they are all using the Earth-centric framework. Okay, 地心坐标系. Oh, I didn't write it down. 地心坐标系. I believe most of you should know it. It's using the center of the Earth as the origin, so that's the ECF, or that's the ECF. Eventually, we want to transform the observation vector to the ECF coordinate system. But right now, here, line of sight system is inside the camera. It's inside the camera. So we need to transform it to the ECF. How? How to transform that? First, we are not directly transform the camera, the line of sight system to the ECF system. We are not doing that. We transform the camera system to the satellite body system first. Alright, we transform it to the satellite body system. First. The whole satellite body it has a defined coordinate system. The whole thing, it's not only talking about. We are not only talking about the camera. The camera has its own system, like the line, which is the line of sight system. But the whole satellite body has one coordinate system as well. And the relationship between the camera system with the whole satellite coordinate system, it has the transformation of the instrument bias, right, which is called the instrument bias. In Chinese, it's called 仪器偏差角. So it's it's a rotation. It's a rotation. So you have the raw pitch yield of here. Raw pitch yield is another description of omega phi kappa. So basically they are the same type, it's just different name for that. And so just omega phi kappa, like that. Alright, so it's the same name, the same type, raw pitch yield. So the raw pitch yield is actually also the omega phi kappa. You can say the x-axis rotation, y-axis rotation, and z-axis rotation. So like that. So in this case, in order to transform the the observation vector in the LLS system to the observation vector in the body system, we need to perform three rotations. We need to perform three rotations. It's similar to like the omega phi kappa rotation that we introduced before when we tried to derive the collinearity condition equation. So here we need to perform the like raw pitch yield rotations over here. So and then of course as you can see here is originally from the LLS system, and after the transformation then you can have the observation vector in the body system, in the satellite body system. And this MP1 multiply MR1 and multiply MY1 is, after you combine them, like the rotation metrics, right? So, and you can and we call it M bias, the rotation metrics from the instrument bias. Okay? So with these two steps, first, let me repeat it again. So first, originally, you have the image and you're pointing at a certain pixel which has the sample and line. And with that sample and line, you can input into the LLS third order polynomial function to have the state vector, so to have this observation vector inside the camera system, And however, camera is just one component of the satellite. And so these this observation vector inside the camera system needs to be transformed to the observation vector described as the with the satellite body system. So how to do that? We can use the instrument bias rotation metrics to do it. So the U LOS can be transformed to U body. Right, that's the observation vector by describing with the body system, satellite body system, satellite body coordinate system. Okay, and with that, then the body system needs to be transformed to the ECF. Right, it needs to transform the ECF to the ECF because the satellite body system, it has origin inside the body, inside the satellite itself, inside the satellite. So how to transform that? That part is easier. That part is much easier. It's just the satellite attitude. So we have the EOP with XC, YC, ZC, and omega phi kappa. And here is the omega phi kappa for the EOP of the satellite. So you have the raw pitch yield, raw attitude, pitch attitude, and yaw attitude. So your U body, the observation vector described in the satellite body coordinate system, can perform a series of coordinate transformation, and then eventually, after that, you can transform it to the ECF system. You can describe the observation vector in the ECF system. So the MP1 multiply MR2 and multiply MY2, and it will be, we can call it the rotation matrix of the satellite attitude, M82. Okay. So in this case, the whole series of transformation is from the sample and line pixel, from a single pixel, transform it to U line of sight, to U body, to U ECF. Okay, to use ECF. And this use ECF is what you need over here. Is directly what you need over here. So I believe you guys can say it right. So this U is actually the U ECF I write over there. This one is that one. Because as you can see, U line of sight u line of sight multiply m bias, and then multiply m entity, and then you have the u ECF, and which is this large U vector over here. Okay, any question till now? This is a little bit advanced, and like I said, it's not well, usually mentioned or usually introduced in this detail, actually, in this detail. So some of the, lectures, they will talk about these equations, but however, may not be those details explanation. Yeah, so hopefully by introducing this, it can help you to understand how exactly does it work if you are talking about the imaging geometry for satellites. For satellites. And what I want to say is that, like I believe 2 or 3 years ago, right about the time that the Formosat 5 is going to be launched, and well, they are trying to solve those, for example, the LOS polynomial function coefficients, because the satellite company, they need to provide these two. They need to provide, actually, they need to provide these transformation coefficients, and of course, the satellite altitude that can be measured on board. This can be measured on board. And these two, of course, is about IOP. So this part is about IOP, and this part is about the whole mapping system. So these two can be measured before launching the satellite, and they can be pre-derived. You can derive those coefficients, but however, during the process of launching, or you can say launching the satellite, the vibrations actually could damage the satellite. It could damage the satellite, and so after you launch the satellite, you need to perform the onboard solution again. You need to try to understand you need to confirm whether those coefficients has been changed or not. So at that time, the NSPO, the National Space Organization, they were trying to solve those coefficients. Okay, so there's a series of process to do that. Okay. Okay. Any questions? Oh, yeah, it's quite dry, huh? Not very easy to swallow. But well, that's you can say I kind of intentionally put all the discussion or all the introduction of the satellite imaging geometry or satellite photogrammetry to like the very end of the lecture. Is this kind of more advanced and a little bit different from. Actually quite different from the traditional era of photogrammetry. But however, if you take a look at this, it's kind of like they can simplify that. Although it looks scary in terms of all the equations, all those relationships between those vectors, it may look scary. But however, in fact, it's more. It can be more simplified compared to the aerial photogrammetry, like with the characteristics of the small FOV. Okay, so that's the discussion over there. There's one other thing I want to tell you guys. As you can see, we could usually earlier. Alright, let me just mention the term. The term is about direct georeferencing. It's about direct georeferencing. In Chinese, it's called 直接地理定位. So the process of that. Originally, we were talking about, say, if you want to perform for example, the space intersection, then of course one of the necessary information is the EOP. Is the EOP, and that EOP can be from the space resection. You can use some ground control points to derive the EOP. But however, right now, most of the mapping system, they also have the EOP from sensors. Right? They have usually they have EOP from sensors. Maybe from GPS, maybe from IMU. So those are, and doesn't matter, it's a satellite or it's an aircraft or even a UAV.